Hi everybody, Ms. Suchi here. We are going to be covering section 6.2 in geometry, and this is talking about chord properties. Our objectives today: I can discover the properties of chords to a circle and practice my construction skills. Now, we are not going to be doing construction skills per se. This is a section that we skipped due to limited time, and so with this lesson, we are not going to be doing any constructing of chords, but we will talk about the properties of the constructions. All right, in investigation number 1, it says draw an example of each term. Now, in the previous lesson, we talked about a central angle. So we can reflect back and draw what a central angle looks like. So first we have our circle with our center point. And to be a central angle, the vertex is at the center of the circle, and the sides are the radii. So I'm going to start with my corner at the center and have it open up kind of like a Pac-Man mouth. So I've got two sides of my central angle. Those are both radii. Now, because my circle is not perfectly drawn, you can see it's kind of slanty here. It looks like these two radii are different lengths, but they are in fact the same length because they both start from the center of the circle and go out to a point on the circle. All right, next one. This is a new one. This is an inscribed angle. And in this particular word, the vertex is actually on the circle. And that's like the edge of the circle, but we don't officially call it the edge. It's just the points that are making up the circle itself. So here's our circle. Well, that one's much better. With the center. And then inscribed means my corner has to be along this outer rim. So I'm just going to pick a point along the outer rim here. And then when I draw in my sides, the sides are actually going to be chords. So they're going to start from that vertex corner and they're going to go across to another point on the circle. And then I'm going to make another one going across. Now these two chords, because they're going to different locations, they are not going to be the same length necessarily. They could be depending on how they were positioned in the circle, but they don't have to be. Now I'm going to draw another example of an inscribed angle because this one does not surround the center point, but if I positioned it differently, it could. So here is another example of an inscribed angle. Oops. So here you can see my angle is positioned where it looks like it's eating the center of the circle. So as long as you have your corner on the edge and then your sides go all the way to another point, that's called an inscribed angle. All right, investigation number 2, properties between chords and central angles. So the first thing says, on this circle, mark that BA and DC are equal. So BA and let me straighten that out there. DC are equal. Now to mark them as equal, I have to use hash marks. So I'm going to put in 2 hash marks on each of these, showing that they are the same measurement. The second part of this question says, why are AO, BO, CO, and DO all the same size? And the reason for that is because they start on the edge of the circle and go to the center of the circle, they are all radii. On that same circle. So no matter what direction I draw out from the center to a point on the circle, that radius length is going to be the same. So I'm going to put a single hash mark in each of those, showing that those are the same. All right, now if we think back to chapter 4, chapter 4 is when we had triangle congruency. It says, what congruency shortcut makes triangle ABO equal to triangle CDO. And technically, we would make a little congruent sign here. It was probably just the way that the computer was working. It didn't have that option. So why are these two triangles congruent? So I'm going to highlight those two triangles. So ABO, I'll do in pink. ABO, this one right here. And then I'll do the other one in blue, CDO. So I've got these two triangles. Why would they be the same? So looking at the three parts that they have marked as congruent, we have a side marked congruent, another side marked congruent, and a third side marked congruent. So this shortcut would be SSS. When we have two congruent triangles, it automatically means all of their other parts match up because corresponding parts of congruent triangles are congruent. So the corner AOB and the corner COD will be the same size, even though they're not vertical angles in this case. So for the chord's central angles conjecture, it states, if we have two chords the same, like the yellow ones we have highlighted in this picture, AB and CD, then they will determine two central angles that are also congruent. And down in this picture, we can emphasize that as well. So as long as these two are the same size chords, the central angles will also be the same. There we go. All right, our next conjecture says chords arcs conjecture. If two chords in a circle are congruent, so that's the same thing we just had, here and here. Let's mark those as congruent or equal. That last property said the central angles will be the same. This one I don't have the central angle drawn in, but when I do have a central angle, like in this example, if I know the measurement of that central angle, let's say it's 70 degrees, then the intercepted arc, remember, is that same measurement. So if my chords are the same, the central angles would also be the same, which means that the intercepted arcs will also be congruent. So this arc, LM, would be the same size as this arc, XY. So their intercepted arcs are congruent. And here you can see the statement there. LM, the yellow segment, is congruent to XY, the other yellow segment, or the chord, I should say. Then the arc LM, pink here, is congruent to the arc XY in pink here. So anytime we're looking at chords, arcs, and central angles, they kind of all go together. So if we know, excuse me, that the chords are the same, then we automatically know that the central angles are the same, and that also lets us know that the arcs are the same. Great. Investigation number 3. All right, properties between chords and the center of the circle. So looking at this conjecture, perpendicular to a chord. Let me zoom out a little bit here. So it says the perpendicular, which is the 90 degrees, from the center of a circle to a chord is the blank of the chord. So let me look at this chord. Here is our chord. And it is perpendicular as shown right here. And it does connect to the center. So if I look at the chord, what else is this perpendicular line doing to that chord? And if I look at the statement above, it says CB is congruent to BC. And that's because of these two hash marks. So by cutting through this chord at a 90-degree angle and hitting the center, it's actually folding this circle exactly in half, which means that point B here is the midpoint from C to D, or this chord is getting bisected. So the perpendicular from the center of a circle to a chord is the bisector of the chord. And then I'm going to make a little note here that point B is the midpoint of CD. Okay, now the key here is that it must pass through the center. This is super important. If it was going anywhere else perpendicular, it wouldn't be folding this circle perfectly in half, so then B would not be the midpoint. So it must go through the center when crossing at a 90-degree angle for this to be true. Okay, this next picture says, given that AB is equal to CD, so let me highlight those. Okay, now those two are chords. And with chords, we know that the central angle then will be the same and the arc will be the same. So I could highlight the arc as well. Okay, the next piece of information they give me is that angle E is 90 degrees and angle F is 90 degrees. Well, here's point E, so that's a perpendicular 90, and here's point F, also a 90. So now I know for sure that because this GF connection hits the center and it's hitting at a 90 degrees, it is cutting this segment DC in half. The same thing can be said for the segment AB. Since E is getting hit at a 90-degree angle and it's connected to the center, this one is also cut in half. Now, because these chords were originally the same length, these halves are going to be the same size as well. So I'm using the same hash marks on both pieces. Okay, we've got all the information now, and it says measure EG and FG. So if I were to measure, whoops, here we go, E to G and F to G, they are going to come out to be the same length. And that's because the chords, being the same measurement, have to come into the circle the same distance. And so that distance to the center will also be the same. So I'm going to put a single hash mark in each of these, showing that EG and FG are congruent. So down in the conjecture, it says two congruent chords in a circle are blank from the center of the circle. So remember, our yellow chords up here were the congruent ones. They are the same distance from the center of the circle. And the word for same distance is equidistant. Wow, that's a lot of information regarding just one pair of congruent chords. Investigation number 4. Where is the center of the circle? Well, it's not drawn on there for us. I know it's somewhere around here. And then the second piece of information here says these chords are not equal in length. So they would not be equidistant to the center of the circle. But because I know if we are crossing at a 90 degrees, connecting to the center, it will cut that segment in half, or that chord in half. I just need to find the halfway point of each of these chords. So I'm going to take my marker, and I don't have a ruler with me, so I'm going to approximate that this looks like the middle. And to emphasize that I'm believing that is the middle, I'm going to put hash marks. And I'm going to approximate on CD as well. This one looks like the middle, so I'll put a different set of hash marks this time because the chords are not equal in length. And then I'm going to take my straight edge. And the reason I'm taking my straight edge is because I need to have a pretty close approximation of where the center is going to be. Now, to make this perpendicular, I do want to cross it at a 90-degree angle. So I am approximating that angle measurement. Remember, you can bend it different ways, but you want to try and get it to be a 90-degree corner. So if I was going to add in that information, this appears to be a 90-degree corner here. I'm going to do the same thing through the other midpoint. I'm going to approximate a 90-degree corner. Now that we have both chords with a perpendicular bisector, those chords, in order to be a perpendicular bisector, must pass through the center. So this common point between them must be the center. So let me write out my steps I did on that. First, I found each chord's midpoint. Second, I drew in the perpendicular along the midpoint. Third, the center point is where the perpendicular bisectors cross. So down here in the conjecture, it says the perpendicular bisector of a chord, and then it has blank. And we want to say that the perpendicular bisector of a chord always passes through the center of the circle. So here you can see on the picture, that's a 90-degree crisscross, hash mark, hash mark. This would be the midpoint right here. So as long as you are crossing through the midpoint at a 90 degrees, it will always cross through the center. All right, here are some summary questions to practice these pieces of information, these conjectures, on the following day. Thank you so much.